Good morning, good afternoon, good evening, everyone, wherever you are in the world. Welcome to our ChemDraw Connect webinar series. My name is Nicolas Tribello. I'm marketing lead for chemistry here at Revity Signals, and I will be your moderator for this session. This ongoing ChemDraw Connect webinar series is an opportunity for you to learn more about ChemDraw's features to effortlessly create, represent, and report your chemistry and make your research shine. Today's topic is design natural and artificial peptides and oligonucleotides with ChemDraw, advancing your molecular design toolkit. A couple of housekeeping points before we jump in. This session is being recorded and will be available for streaming at revitysignals.com/chemdraw-connect. Please submit your questions during this session through the question panel located on the top of your screen. As always, we want to hear from you. If you have any topic suggestions for upcoming connects, feel free to reach out to us on signals.events@revity.com. Now, I would like to introduce you to our speakers for today, starting with my co-presenter, Lindsay Rickershauser. Lindsay holds a PhD in organic chemistry from Johns Hopkins University under Professor Gary Posner, when her research focused on the synthesis of anti-malarial therapeutics, as well as developing synthetic methodologies. From there, she specialized in the synthesis of stable labeled isotope molecules in the clinical, diagnostic, and forensics testing industries. She turned her focus to the area of cheminformatics in 2017 when she learned to develop, commercialize, and launched a leading retrosynthetic software. Having joined Revity Signals in 2022 as the ChemDraw product manager, she continues to strive to deliver values and innovation to chemistry around the world. On my side, with 17 years of experience in drug discovery, I've provided direct project support and led teams, but also played a significant role in establishing scientific standards and ontologies at my company. I hold a master's degree in chemical engineering with a specialization in organic chemistry, a PharmD, and a PhD in drug design from the University of Paris. Our agenda today will be divided into main parts. First, there will be an introduction about representing complex molecule using a standard called HELM. I will tell you a bit more about the story behind it and what it is. After I've done this introduction, I will pass the baton on to Lindsay, who will show you directly within Signals ChemDraw how you can represent these complex biomolecules. So what was the technical challenge that people wanted to tackle with this particular HELM standard? So imagine you're a chemist working with such complex biomolecules, and you would ask typically the question whenever you want to represent it, report it, or register it as a molecule, as a compound, but how can I represent this complex biomolecule without having to draw an all atom structures? You can imagine that if you want, for instance, to represent a peptide after a few residues already, you will have drawn several tens of atoms, which can be a bit painstaking if your biomolecule has several tens of those residues, right? So there should be a better way than having to do an all atom structure representation. And this is the kind of challenge that people at Pfizer wanted to address in the early 2000s as they were developing such biomolecules for being potential drug candidates, right? So that was originally designed at Pfizer. They actually published in the Journal of Chemical Information and Modeling this seminal paper that described for the first time what the HELM standard was. Obviously, if you want to have a standard being used not only across your labs, but across an industry, it is better to reach out to other people within that particular industry. And that's exactly what scientists from Pfizer have done. While they have reached out to other pharma companies through the so-called Pistoia Alliance, which is a consortium of pharmaceutical and biotech companies who can decide together on what a standard should be, for instance. So that was an effort, that was a project that was ongoing between 2008 and 2014, where they actually made public what the HELM standard should actually be for everyone to use. Later on, as of 2021, the IUPAC itself actually established a HELM subcommittee to oversee the partnership between the Pistoia Alliance and oversights the ongoing efforts. So what is HELM? So HELM is actually a line notation to represent this complex biomolecules biopolymer. HELM stands for Hierarchical Editing Language for Macromolecules. And you can see from this little pyramid, this is actually representing this particular hierarchy. At the bottom of it, you have the all atom representation for residues, for instance, here. So I've represented a couple of amino acids as well as a ribose molecule. So these molecules, you can represent it differently, symbolizing them, right, by a certain coding system. Like alanine, for instance, would be represented by an A. Ribose could be represented by R. And as you can see, you have to append it links to these residues, or you can even have 3 for the case of ribose, which allows you to do chemistry with those residues. Of course, one of the first things you can do is to create a simple biopolymer with it, like a peptide or an oligonucleotide, and that's what you see here represented in blue on the right hand of your screen. Eventually, if you connect together these polymers, you would create this so-called complex biopolymer. And here what you see in this tile box is actually on the top is actually a peptide that is connected to an oligonucleotide at the bottom through a chemical linker represented by this orange box. Before we go into concrete examples presented by Lindsay, I would like to have a quick reminder. So ChemDraw exists in 3 different offerings that are adapted to your needs. We have ChemDraw Prime, which contains all the core functionalities, ChemDraw Professionals, and Signals ChemDraw. ChemDraw Professionals and Signals ChemDraw are the 2 offerings that are enabled with HELM. There is actually even more HELM features within Signals ChemDraw, and it is the reason why all the examples that Lindsay is going to show you in a few seconds are going to be done with the Signals ChemDraw to show how advanced are the functionalities within our software. With that, I will hand the baton on to you, Lindsay, to present how seamless integration we have for HELM within ChemDraw.
Wonderful. Let me just take the screen. All right. So before I jump into the software today, I want to give everybody just kind of a level set of where we started with HELM and get to then where we are today. So you may be surprised to know that actually being able to draw and represent biopolymers in ChemDraw was already possible way back in 2017. That's when the first capabilities were actually launched into the ChemDraw desktop editor. And so since then, with each major release since then, we have made significant improvements, enhancements, and expanded the capabilities in the toolset in that area, with a lot of those capabilities being released into the Signals platform within the last year or so. And so I'm really excited to be showing you some of that. So what are the capabilities that we have, right? So in ChemDraw Desktop, when you're thinking about ChemDraw Professional as well as Signals ChemDraw, you have HELM editor sort of editing support. And what does that allow you to do? That allows you to draw things like peptides, oligonucleotides, any sort of conjugates with those chemical linkers that Nico just showed you, comprehensively within that desktop application. Not only that, you have like full copy and paste support to be able to get those sequences in and out of ChemDraw specifically, with languages such as FASTA and HELM being supported. And you also have monomer management capabilities. So where you are drawing oligonucleotides or peptides that have customized monomers that aren't standard. So it's not a standard alanine, it's not a standard thymine, nucleotide, those sorts of things. You also have the capability to manage and create your own custom monomers for use. All of those things included also mean that the ChemDraw CDX and CDXML formats are fully portable, meaning that when you use these monomer libraries, even those custom monomer libraries to draw your biopolymers, this format is fully portable. So you don't necessarily actually need that custom monomer library to be able to parse what's in it. All of that information lies within that ChemDraw document. So, think if you're collaborating, collaborators will have those structures. They don't have to have that sort of originating library to pull from. Okay. Within visualization, right? So early on in Helm visualization in ChemDraw, we had sort of text kind of labels that were being used to render these complex biopolymers. However, that was quite difficult for then users to parse the differences between the monomers and polymers that they were actually drawing, right? Could you have differences between peptides and oligonucleotides? And from a text-based format, that kind of makes it hard to parse. And so with version 22 of ChemDraw, we actually changed that label text format and transformed it into a sort of graphical cartoon format. So we actually created a little bit more visual representation of these polymers that allowed you to decode really naturally and easily the difference between peptides, oligonucleotides, and any sort of chemical linkers you may be using. So what you see here on the screen is the exact same representation, the exact same biopolymer, but now in this graphic format. Those polymer shapes are indicating, the graphic shapes are indicating the polymer type that you are using. So circles are peptides, squares are chemical linkers, and then you have the various shapes for ribose, phosphate, and nucleobases. In addition to that, you have color coding of these monomers. So where you're using custom monomers that may be relating back to, say, cysteine, you have color coding based on the natural monomer that they originate from. So you can quickly and easily see any custom monomers based on the symbol that you're using inside of that graphic, and then the color representing that natural monomer analog. So you may or may not have seen this representation already, but this was released back in around 2022, 2023 timeframe. Since then, we have been working on significantly expanding these capabilities, and we have also rolled these capabilities into Signals ChemDraw and provided web editing capabilities and an application that's provided with Signals ChemDraw called ChemDraw Plus. If you're not familiar with ChemDraw Plus, this is an application where it's fully web-based without a desktop installation. You can go create, curate, and manage your chemical drawings directly in a web browser. And so this HELM editing capability was significantly built out inside of this ChemDraw Plus application to allow not only the same functionality that's available in desktop, but additional advanced features and functions as well. And so now you have the HELM editor that's available in this editor that allows you to do additional things, not only just draw with the HELM editor itself, but to catalog, favorite monomers. So think about additional, monomers that are custom that maybe are quite long in terms of symbol and hard to find in a very large library. You can catalog that as a favorite and access it on a single tab within the application. In addition to that, you have quick and easy text insert. So you can insert a HELM string, a FASTA string, a build string into the canvas quite easily using a text tab. And then you have, editing capabilities depending on the polymer type that you're creating. So peptides, DNAs, RNAs, and then those chemical linkers and blobs as well. Additional capabilities in the platform. You also now, with that graphic representation, a lot of times scientists will want to see that structure that's behind that graphic, and that's totally reasonable. That's something that we all want to do. one thing that you have in the platform, and I'll show you in just a second, is the ability to hover over any one of those graphics in the platform and get a hover over preview that actually allows you to see exactly what that structure is. You also have expansion capabilities, so you can see that structure on the canvas. So I think you're seeing this nice biopolymer representation. I believe that's tirzepatide, which is an FDA-approved drug that has this hybrid representation of that graphic rendering of that peptide with certain residues and chemical linkers then being sort of expanded to that full structural representation. And in the recent past, we've also rolled out new capabilities around oligonucleotides. So being able to create a duplex with complementary strands. We've also improved the editing capabilities inside the platform and really some really cool stuff that I'm excited to show you. One last thing before I jump into the tool. So in the Signals platform, you can't use those monomer libraries that you're creating in ChemDraw Desktop, but you do have centralized libraries in the Signals platform that are available once you activate them to use in the ChemDraw Plus application in Signals ChemDraw. So the centralized monomer library application is called HELM Monomer Curation. It allows you to import custom libraries for use in the platform. This is an application that is controlled through roles and privileges within the Signals platform. So if you have questions about that, you can always ask, but this is really configured typically by an administrator in the Signals platform for use. However, there are still Signals monomer libraries that are available to users even without the use of this custom functionality. Okay, so with that, I'm going to go ahead and jump into the platform. I'm going to show you some of the different kinds of biopolymers you see here on the screen. Most of what I'll be showing you is how to sort of quickly and easily draw peptides, oligonucleotides, and some of the different variations therein within today's demonstration. So I'm going to go ahead and open up Signals ChemDraw. So I am right now in the ChemDraw Plus application. This is where I can create and manage all my drawings here directly in the Signals platform. As a user, I can, of course, create any drawings that I want. I will save those into notebooks inside of here, and I'm just going to go ahead and quickly create a new drawing to go ahead and play with it for purposes of today's ChemDraw Connect. Can't type at the same time. So for today's demonstration purposes. Okay, so how do we access that HELM editor? So when I create a new drawing here in Signals ChemDraw and ChemDraw Plus, what I'm seeing here is a really clean canvas to go ahead and get started. You may or may not be familiar with this new editing experience. So right now I have all of my drawing tools down the left side of my canvas for use and access. And in fact, the HELM editor is right here on that left-hand side. If I open up that HELM editor, what that's going to do is that's going to show me all of those sort of tabs that you saw in that PowerPoint presentation to be able to start working with. So I can draw my peptides, I can draw my oligonucleotides directly from here. I also have this text tab. This text tab, like I said, also allows me to quickly and easily get information into the canvas. So coming in here, I'll show you how we can just very quickly and easily get started. We have different monomer libraries that are available to us. The ones that are automatically activated on the platform when HELM is activated on Signals ChemDraw are our natural monomerless library, a Pistoia Alliance monomers library, of common sort of customized monomers out there, and then a Signals monomer library that contains additional monomers that were originally part of the Pistoia Alliance monomer library and are out there and in the published literature. So when you start looking through these, what you'll see is that you have, in this peptide tab, you have different filtering options, but when you start getting to more than 50 monomers within that HELM editor, what you see is you have them actually categorized by the natural monomer. You can see that color coding really easily. Now, if I wanted to start going ahead and building something, all I have to do is click on the canvas where I want to start drawing, and I can start using those HELM monomers. If I start pressing those monomers, that will add it to the canvas. Now, I also still have the capability to additionally draw in on the canvas using my keyboard, right? So we also have these hotkey sort of capabilities. If I want to add a monomer from a library I'm viewing, I've switched now to the natural monomers library. I can simply type on the canvas, I just typed C, that will add a cysteine residue, and I can continue to actually put those residues on the canvas simply using the keys on my keyboard. These hotkeys will only work for a single symbol monomer within a library. So multiple, monomers that have multiple characters for their particular symbol won't necessarily work this way because it's multiple characters and you can't type a single key to get to it. Now, once that I've drawn this, I can actually navigate now throughout my sequence as well. I'm using the arrows on my keyboard to go back and forth, and you see that gold box that actually puts the monomer in replace mode. So if I made a mistake, this is not the monomer that I wanted to add to the canvas. This is aspartic acid. Maybe I want something different. I can simply type an alternative monomer symbol and replace that and continue on editing my sequence. In terms of getting more complex monomers onto the canvas, or sorry, biopolymers onto the canvas, I can come in and use the text tab. So I have multiple different sequence types that are supported. So if you have something like a HELM string of a rather complex sequence, you can use that to actually just get it into the canvas and continue editing. So I'm going to just go ahead and paste a HELM string into the text tab here. I can insert it on the canvas. And now let me just go ahead and zoom to fit. That immediately inserts that sequence onto the canvas for me to continue editing. HELM strings are sometimes still hard to find for even standard sequences that are out there. Some places that you can go to find them is PubChem, sometimes Wikipedia, for things that are out there and published in the literature, or registered compounds, maybe they're FDA approved drugs. You may or may not be able to find them. This is still an evolving sort of adoption of people out there and in the industry, and so it's kind of hit or miss whether you will get that. The one great thing is once you draw this in ChemDraw, you will be able to get the HELM string and you will be able to catalog it. So if I actually select this HELM string on the canvas, I have a copy as HELM option, and I'll just paste it back here into the text tab. You can see that I have that, and I can keep that and record it for use in the future as well. Now, I also have other options in terms of getting sequences onto the canvas. I'll switch over to FASTA peptide. If you're unfamiliar with FASTA, FASTA are the single letter representation of sequences. It's used in both peptides and RNA and DNA. So you'll have to make that selection between which FASTA you would like if you're inserting from the text tab. And here I'm just going to go ahead and paste in a quick FASTA sequence of vasopressin, which is an antidiuretic hormone and sometimes used in the treatment of things such as diabetes. So I'm going to go ahead and insert that onto the canvas. And now I have, very quickly, very easily, I have my entire sequence. Now keep in mind, these sequences have all atom representation sort of underneath that graphical rendering, and I can get to any of that information quickly and easily as soon as I want it. So if I only just want to see what that structure is, you can see I'm hovering over a monomer, and I can see what that structure is. If I actually want it exposed on the canvas, I want to see that within my sequence, I want a hybrid representation, I can do that too. All I have to do is select that monomer. So I've selected it with my marquee tool, and I can use the expand label tool. And what that's going to do is it's going to expand that to the all atom sort of representation of that monomer. Now, if I don't want to keep it that way, I can of course collapse that label right back. I don't have to do that. I can also, let me just show you, I'll quickly clone this entire sequence. I can do this for the entire sequence as well. I can see the entire structural representation. So that's quick and easy to do, and you can do this on per residue basis for the entire sequence as well. The last thing in here that it is representable in the text tab is a BILN string. So if you are unfamiliar with what BILN is, BILN format kind of extends the FASTA notation to include unnatural or custom monomers, and it allows sort of more human readable, human parsable sort of representation of a complex sequence. This is only for peptides and can be interpreted and converted into HELM inside of the platform. So I'm going to go ahead and just paste in a BILN string so you can see what that looks like. You can see this is a little bit more human readable when you're comparing to a HELM string, right? So you see the individual letter indications for those peptides, and you see numbers in parentheses. Those numbers map cross-links in that sequence. So I'm going to go ahead and insert that onto the canvas. And what we see, I'll go ahead and select that and start zooming. Oops, well, a little bit too far. So now you can see this really nice complex peptide, and I can see sort of that mapping with those connection points there. And just to give you a quick comparison side by side, how that's sort of different from the HELM string. The HELM string, it looks a little bit more complicated, a little bit harder for an actual scientist to write out because of the different connections and the way that language has to be sort of written to be able to be parsed correctly. In addition to a smile string, for example, that goes up in another, even one more level of complexity as well. Okay, so that's a quick tour of sort of the base level capabilities inside of the HELM editor and Signals. So let's kind of start using this to build, some different biopolymers. So I have a quick example here of terlipressin. So terlipressin is an FDA drug FDA approved drug that is used for the treatment of hepatorenal syndrome. So let's just zoom in a little bit here to take a look. So the interesting thing about this, right, is it's a rather small peptide. However, if you expand it to the full structure, that takes a rather long time for us to build, right? Even if you're to use all of the shortcuts and hotkeys available in ChemDraw, it's still going to take some time to do it. But I want to show you sort of how we can quickly and easily draw this using the HELM editor specifically. So now I can go through and I can start building using the HELM editor sort of monomers in the toolbar. I can also start typing on my keyboard, and I can go ahead and get that very quickly on the canvas. And so if I come to the end here, I'm going to add an amine to the end of this. This is just an amine, sort of a terminal amine that can be added to the end of the sequence. You can alternatively, if you don't want to draw this as an actual monomer, you can change that terminal OH to an NH2 as well. So now that I've done this, I can very quickly and easily just draw a cross-link and do a quick biopolymer cleanup. And now you can see in the span of less than a minute, me actually talking through this, I have now built that where it would probably take me at least a few minutes to actually draw this physical structure. And I can clone this. If I move around here sideways on the canvas, just out of the way here, I can now also expand that to the full structure. If I don't want to see sort of this visual format, I can, whoops, I'm moving too far on the canvas here. If I want to change this to more small molecule, I can start doing some structure cleanups here. Biopolymer cleanup is going to keep that in that sort of straight biopolymer sort of form, so you can map where those residues were in the graphic sequence representation. But if you want to see like the true small molecule representation, you can also use the structure cleanup as well in ChemDraw. So you can see very, very quick, very easy to go ahead and draw and recreate that sequence. Now, if you want to start adding chemistries to this, right, a lot of times these peptides are going to be built on solid support. So this is a quick reaction scheme that I pulled out from the literature of terlipressin being actually synthesized on solid support with some trityl protecting groups on those cysteines before that cyclization happened. I can really quickly and easily get to that. So let me just go ahead and maybe I will just grab this HELM string here and I'll paste it. Oops, I did a partial. Okay, let's just draw it. Let's go ahead and draw it here. Okay, so I'm going to go ahead and get the precursor here on the canvas, right? Now this is before the cyclization happens and you've got some protecting groups to deal with. You also have solid support. So what I'm going to do is I'm going to change this terminal OH to an NH2. I'm going to now add a bond to it. And I can add a solid support. So how do I do that? So you have in the chemical symbols tool, you have a polymer bead attachment point here. So I can go ahead and add this polymer bead. When it adds, it makes it a little bit short because this is the document settings of ACS 96. Those bonds are a little bit short. So what I can do is I can create that. Now I have my polymer bead attachment. If I want to add my protecting groups to the cysteines, one thing to know is the monomers in the libraries have attachment points that are defined in them. And so on that cysteine, I have an attachment point. That means that I can add something to it on the canvas without making it a custom monomer. Here, I'm going to just go ahead and draw a single carbon off of those cysteines at that attachment point. Now, I can go ahead and select these specific carbons. I can add my trityl groups. I'm just using hotkeys and ChemDraw and shortcuts to add these. A capital P is going to add my phenyl groups. And now I have this precursor of terlipressin, and I can actually now transform that into terlipressin through the chemistries. So that's a quick and easy way to start adding chemistries to these peptides as well. You have sort of this hybrid combination of being able to use all of the drawing tools in ChemDraw and make modifications to these peptides to suit whatever chemistries you're actually doing with them. So that's a nice and easy example. Excuse me. Okay. I'm going to move on now to a little bit more complex antisense oligonucleotide. So I'm going to now look at mipomersen. So this is also an FDA approved drug. This is an antisense oligonucleotide, and it's rather complex. So let me just zoom out just a little bit. And you can start seeing. So these are really non-standard monomers that have been used to build this drug. So you see on the first five, 1, 2, 3, 4, 5, and last 5 nucleotides, you have a ribose modification that is methoxyethyl. Also, throughout the entire sequence, instead of a phosphate, you have a thiophosphate. And then finally, all the cytidines are 5-methylcytidine. So I have highlighted here all of those different modifications along that backbone. So that's very complex in terms of having to build that. But with the tools that we have available in ChemDraw, you can start to put it together rather easily. So I'm going to go ahead and show like how we would actually start to build this oligonucleotide. So I have the DNA RNA tab here. And this DNA RNA tab is a little bit more complex than the peptides because you have other things that you have to do with an oligonucleotide. That's not just a single residue. You have a ribose, you have a phosphate, and you have a nucleobase that you are using to build this sequence up. And not only that, but you have custom modifications within each one. So what we're going to do is we're going to choose here at the top what we're primarily building with. And typically, I wouldn't expect this to change very often, but typically you are going to be building based on the base that you're wanting to use as part of that triplet sort of nucleotide. However, you can choose other sort of residues besides the natural residues for those ribose and those phosphate. And so now that I've chosen this base as the primary driving monomer that I'm going to use to draw with, I now have to choose what my ribose is that I'm going to use to draw with, as well as what my phosphate is. And so I'm going to choose methoxyethyl here. Now, if I didn't have this, so this, this ribose dropdown is going to have the most recently used sort of monomers here. But if I wanted to change it, right, I don't have what I'm looking for in this list. I can go through a change process and I can go through and look in any one of the monomers databases that I have for the different ribose modifications, and I can choose something that's alternative to that, and it will use that. In this case, let's go back to the Pistoia. I want to use the MOE, and I have it right here. So I'm going to go ahead and just reselect this, even though that's already in the list, and I can go ahead and choose it. Now, if this has many more monomers than I can parse quickly here, I do have a search function. I can type in the symbol or the name of that ribose to pull back results as well. So now that I've chosen the ribose, I want to do the same thing for the phosphate. I can go through the same change process here, but I have my thiophosphate right here, so I can go ahead and choose it. So now I'm ready to go, and I can start building those first 5 nucleotides in my sequence. And I'm just going to zoom in so we can kind of start building this side by side. So I'm just going to put my insert cursor here, and I'm going to start building my oligonucleotide. Now I just typed G on my keyboard to insert that first nucleotide because I have a guanine. G is a single symbol. I can use that hotkey. I cannot use it for the 5-methylcytidine, but I certainly can add it directly here. Now I can add my T and my 5-methylcytidine, and that is the first 5 residues of my 20-mer sequence. Now I need to change from methoxyethyl in that modification to deoxyribose, right? So simple and easy change. I can come up here, I can choose deoxyribose from my list, and I can continue building. So I can use those hotkeys on the canvas, and I can continue building my sequence. And I'll just start to scroll over a little bit so that we can see as we're building. Oops, I went a little bit too far. That last one, oops, is a methoxyethyl. So now I've got those middle 10 nucleotides, right? and I need to switch back. So simple, easy, now that we know how to do it, do a quick switch back, and then go ahead and build those last 5 residues of my sequence. So now I have very quickly and easily built a very complex structure. Now again, I can expand that to the full structure. I can expand specific residues if I want. So if I just want to open up and see that deoxyribose, I can do that. If I, for example, also just want to see all of the nucleobases, I can open all of those up as well. So you can sort of choose how you want these things represented. If you're wondering how I added the colors in this oligonucleotide that you're seeing, I can do that by round trip editing in ChemDraw Desktop. So with Signals ChemDraw, you also have, of course, access to the full feature set of ChemDraw Desktop that's available, and any features that aren't quite available yet in ChemDraw Plus, you can choose to open this in ChemDraw Desktop directly if you have that installed as well, and access those additional sort of more advanced features. But I would encourage you to check if you have a Signals ChemDraw license, what's new. We also publish updates on our website of anything that we're releasing that's new in the platform as well. Okay, so that's a little bit more complex oligonucleotide, but it doesn't stop there, right? We still have other kinds of biopolymers that we want to register. So I've shown you 2 sort of more simple biopolymers, and as Nika sort of alluded to, the top of that triangle are very complex biopolymers. So think about chemical linkages, or think about hydrogen bonding between complementary strands. So we do support complementary strands in ChemDraw. And I want to walk you through sort of all of the different ways that that is supported. So let me go ahead and create a new drawing for a new blank canvas to go ahead and walk through. So what is a complementary strand? So you may or may not be aware, so in DNA and RNA, you have a template strand, and often you have its complement. The complement, as we create it in ChemDraw, is always going to be based on Watson-Crick base pairing and those complementary base pairs. So how do you access that, right? So I showed you the text tab and all of the different languages that we support very quickly, very easily. If I want DNA, I can type in a FASTA string. I can also immediately select the generate complementary strand, and ChemDraw is going to insert a set of a template and its complement onto the canvas with hydrogen bond intact. So what you can see here is I've got a strand and its complement based on Watson-Crick base pairing and complementarity. And I can see I have a visual representation of a hydrogen bond between each of these nucleobases. Now, we all know that between nucleobases, there's not just a single hydrogen bond, right? Depending on the base pair, you may have 2 or 3 hydrogen bonds actually represented. ChemDraw actually has the chemical intelligence and perception. Not only is it placing those hydrogen bonds, but you can expand and view those hydrogen bonds as well. So if I choose to instead of look at these complements in this graphic representation, and I want to expand this, it's going to show me the hydrogen bonds between those, the correct hydrogen bonds based on Watson and Crick base pairing, and the hydrogen bonding between those different base pairs. So this is really important in a lot of ways from chemical perception. We also will map those hydrogen bonds, of course, in things like mol files. The hydrogen bond pairing information will be available in those HELM strings when you copy and generate them as well. And so you can quickly and easily get to that. So This is now for natural nucleobases, right? So I've showed you from a FASTA string, you can very quickly, very easily generate that. Now, if I went and decided that I was going to build a oligonucleotide and I still wanted its complement, but it had custom monomers, right? So custom bases that I was using. I can still create the monomers the complementary strand with that. I just have to access a different tool. So let's just go ahead and build a quick sequence here, right? So I have this quick sequence. Now I've got 5-methylcytidine, so those are custom nucleobases. I've got ribose and phosphate modifications, but I still want a complementary strand of this. I cannot do that through the text tab, but I can do this through the context toolbar in ChemDraw Plus. So I have this tool when I actually select an oligonucleotide that will show up on that context toolbar based on what I've selected. It's called Generate a Complementary Strand. And so if you have any custom oligonucleotides that you still need that complementary strand for, you absolutely can create it using that Generate Complement tool. And as you can see, I'll go ahead and expand that as well. We're still mapping those hydrogen bonds. And it is mapping it based off of sort of the natural analog that those residues, those custom modifications sort of map to. So in the case of the 5-methylcytidine, of course, it maps back to cytidine, so you should see the appropriate hydrogen bonds as long as the hydrogen bond acceptors and donors are still present to provide those hydrogen bonds mapped between those sequences. There's one additional way that you can also actually pair and get complements. And so that is called the auto pair function. And I have a quick and easy example of that as well. So there's an FDA approved drug that's out there on the market. It's called Patisiran. This is an siRNA, which is a set of strands that are hydrogen bonds and complements of each other. So I'll just switch back here. So Patisiran, this is kind of what it looks like. It's got an overhang here on each side, but it has a set of complements in between. So what do you do in ChemDraw if you have these two strands and you need to actually get them hydrogen bonded together? Well, there are a few different ways that you can do this. So I'm going to put two strands here and on the canvas. I'll just zoom out a little bit to sort of get this on the screen for us. So that's the first strand, and now this is the second strand. So what can I do here, right? I can quickly and easily select this. I have something called now an auto pair tool. So I don't necessarily want to generate the complement of this entire strand because it wouldn't necessarily be correct. I have overhangs as part of this siRNA, right? But I can build both of these sequences separately, and I can go ahead and select them, and I can say, hey, ChemDraw, find the maximum overlap in complementarity between these two strands and place the hydrogen bonds for me. And so I have this auto pair capability, and it will find all of the hydrogen bonding base pairs. It will map them. It will actually orient both of those strands correctly. And what you can see is I have these two overhangs correctly there. Now, if you have a little bit of a smaller sequence and you don't want to use the auto pair, or it's just easier and quicker to draw those hydrogen bonds, you absolutely can. So I can just come here. Let me just delete these few, hydrogen bonds between these nucleobases. If I have already drawn these, I've lined these up. It's just a few, hydrogen bonds I want to place. I can also do that manually, right? I can select the hydrogen bond tool. I can click from one nucleobase to another, and I'm going to appropriately map those hydrogen bonds as well. So I have lots of different options and different ways to be able to get to that on the canvas. And let me just go ahead and zoom out. And we can go ahead and clone this. So I'm just pressing the control key on my keyboard and dragging this down and dropping it on the canvas to create that clone. And quickly and easily, I can get to that full atom representation just by selecting the expand tool. And that's going to take a second. There we go. And now I have that full atom representation. And if I want to beautify it to sort of highlight where all those different modifications are, I can, of course, go into ChemDraw and do a round trip edit. That, I think, is everything that I planned to show today. So I will go ahead and wrap it up and see if we have any questions.
Thank you, Lindsay. Indeed, we have quite a few questions. I've been trying to answer to some of them already, and I've kept a
Okay.
few also because I think they will be of interest to everybody. So there's a couple of questions actually on the not really the level of complexity, but the size of the monomers. What is the
Mhm.
maximum number of residues? Can I draw a complex structure protein, for instance, albumin?
We don't have a maximum number of residues that you can draw, but just I would say consider that ChemDraw is really, built for small molecule and sort of the HELM sort of level structures, right? What HELM was really created for, which was the middle space between small molecules and very large things like antibodies, proteins, etc. So we have, of course, improved performance on larger sort of sequences, but I certainly, if I was trying to draw a very large protein, I may think of alternative ways to represent that when I don't necessarily need the all atom structure underneath it. So you'll start running into things. There are number of atom limits for things that ChemDraw will actually do in the platform. And so if you hit over 7,000 atoms, you'll stop getting things like properties calculations and things like that because those start to get too big and will degrade the performance to a place where you might be waiting a little bit too long to get that information.
Thank you. Another interesting question is, can you search for monomer by drawing the structure if the acronym is unknown, for instance?
That's a really great question, and the answer to that is not yet, not in the Helm editor itself, but stay tuned. That's something that we definitely recognize as something we want to add in terms of capability. Today, you can search based on the monomer symbol and the name.
All right. Another question, can ChemDraw Plus still accept a name such as semaglutide and draw this for you?
That's a really great question. Yes, it can accept name, so we do have name to structure. But today it is somewhat limited in terms of the database that it pulls from, but we do have plans to significantly expand it in the future. But name to structure is certainly there, so you can input a name. If it exists in the database, it will actually, draw it for you, and you can also generate a name for a structure that you draw on the canvas as well.
Thank you. So suppose you do auto pairing with a single strand. Will that create a hairpin?
Great question. Not yet. That is in the works, though. That's something that's in process, and we hope to extend in terms of the capability in the future.
Thank you. Could you attach peptides HELM to oligos HELM and generate the conjugate?
Definitely, yeah. So it just depends on what you want to do. So let me just come into maybe I'll come into this document. So you can do all kinds of different things, right? So say I wanted to connect this peptide to this oligonucleotide, I can actually just go ahead and draw a connection. It's going to tell me, so this is a really great, something that I didn't even get a chance to show. It'll ask me and walk me through the process of actually, how I want to connect these. And so these are kind of large molecules, but what will happen is it'll expand and show me the attachment points available. On this ribose, I have a single attachment point, but you can see I have two possible points on this peptide that I can attach it to. I can select one over the other if I'd like. In this case, I still want it to be a backbone linkage to that peptide, not an attachment, from a side chain. So I'm going to create that. And once I do that, if I go ahead and clean the biopolymer, it's going to now create that conjugate. Now, I can also do this with chem linkers as well. So I could have inserted a chem linker in between that as well. All of that's supported and encouraged to use inside of the HELM editing functionality in ChemDraw.
Thank you. Another maybe special question. When I try to contract an oligonucleotide strand, I get a pop-up box that says, enter atom label to contract to. Why doesn't it automatically contract? This feature worked for contracting my complex peptide, a 21 mer versus a 17 residue peptide.
That's an interesting question. I guess the question would be, how was that drawn? This may be more of a troubleshooting question, to be honest with you. If a sequence was drawn using the Helm editor, expanding it to the all atom sequence and contracting it shouldn't have any problems. Where you may run into problems if you have used a smile string, for example. You cannot convert smiles into Helm and expect that to work. You want to be using the Helm functionality, and as long as you're doing that, that typically should work. If there's still a problem, I would recommend reaching out to our product support team to troubleshoot.
Thank you. Why there is no library in my Helm editor? Does it need to be activated?
If you are looking in ChemDraw Plus, yes, in the Signals platform, Helm has to be activated. That can be done in Signals ChemDraw by an administrator. So I recommend reaching out to your administrator to get that activated and to set it up such that you have access to those monomer libraries. There is help documentation for administrators on how to do this, but if you experience any issues, again, our product support team is there to help as well.
All right, and I think we have one final question. Any plans to represent some of the components in 3D?
That's a really great question. There is a limit in terms of the number of atoms in ChemDraw today of a structure that will do sort of 3D representation and 3D cleanup. That limit exists. So anything under that atom limit, I want to say it's 500 atoms, I think. Um, Anything under 500 atoms, it will do a 3D representation. You can do a 3D clean on it. Anything over that, even with small molecules, ChemDraw is not going to support that.
All right, so I don't think any more questions coming. So with that, I would like to say a big thank you to you, Lindsay, for this presentation and for everybody for their time and interest in the topic of today. Thank you.